Hello everybody. In this video, we're going to learn about linear functions. We've talked a lot about vector algebra, and the two most important operations that you can perform on vectors is vector addition, so calculating vector v plus vector w, and scalar multiplication. If you have some constant number c, multiplying that number times a vector. Now, we're eventually going to turn our attention to functions on vector functions. A vector function is a function that takes a vector as input and then returns a vector as the output value. And it's going to be really helpful for us to identify and work with just vector functions that simplify nicely with respect to these two operations. In particular, I mean that if we have a vector function f and we're calculating f of v plus w, it would be great if you could break that up over addition and say that was equal to f of the vector v plus f of the vector w. Similarly, it would be really helpful if we were working with functions f such that f of c times vector v is equal to c times f of the vector v. Any function which satisfies these two equations, they're sometimes called the linearity equations. Functions which satisfy them are called linear functions. And really, this is a reasonable set of properties to want to work with. It's similar to things you probably saw in calculus once upon a time. For example, if you're calculating the derivative of a sum of two functions, you naturally want to break that apart into two separate problems, and you can apply something called the sum rule for derivatives, right? The derivative of f plus g, where f and g are functions, is the derivative of f plus the derivative of g. Similarly, there's the constant multiple rule for derivatives that says if you're calculating the derivative of a constant times a function, that's equal to a constant times the derivative of a function. And after you do enough calculus, these rules just become automatic and you just use them without even thinking about it. And similarly, when you move on to calculus 2 and learn about integration, you learn that the integral of f plus g dx is equal to the integral of f dx plus the integral of g dx. And similarly, you can bring constants through the integral sign. The integral of c times f dx is equal to c times the integral of f dx. Right? We just want to identify functions for vector algebra purposes that simplify in the same way. One of the reasons this is really great is the following. So first, we have to remember the standard basis vectors in two-dimensional space, in 2D. We call these vectors I and j. So writing them using column notation, I is the vector 1, 0, and j is the vector 0, 1. So it turns out, this is really important, this is why I've written it in red, if f is a linear function, meaning it satisfies those two equations we just saw, and if you know the values of f of I and f of j, then you can calculate the value of that function at any vector v, even if you don't know what the formula for the function is. Right? If you're given these two values here, right, if you know what the two outputs are going to be, that's all the information you need. Let's see an example. Right, so let's say f is a linear function. F of I is equal to the vector 1, 2. F of j is equal to the vector 3, 1. Right, this information, combined with the fact that f is linear, lets us solve and find the value of f at any vector. So for example, let's say we want to calculate f of the vector 4, 5. Well, the first thing we want to do is write the vector 4, 5 in terms of I and j. Right? And we can do that using our two main vector operations. right? We can write any vectors in R2, or two-dimensional space. We can write them as a combination of I and j. Right? We could separate this out using vector addition. We could write it as the vector 4, 0 plus 0, 5. And then we could factor out a 4 from the first and a 5 from the second. And in summary, 4, 5 can be written as 4 times I plus 5 times j. Now, because f is linear, we can break up f. We can separate out over addition. So this term is equal to f of 4i plus f of 5j. But again, since f is linear, we can factor out constants. So factoring out the 4 from the first term, we have 4 times f of I. Factoring out 5 from that second term, we have plus 5 times f of j. And hey, f of I and f of j, we know those values. F of I we can replace with 1, 2, and f of j we can replace with 3, 1. And now we just have to do some vector operations. 4 times 1, 2, plus 5 times 3, 1. So across the top we have 4 plus 15, which is 19. Across the bottom we have 8 plus 5 is 13. Right, so you can calculate the value of this function, which in this case turns out to be 1913, even though you didn't know a formula. You just know these two really important values. As another example, right, same function f, right, and we know that f is linear. F of I is 1, 2, and f of j is 3, 1. Let's say we want to calculate f of 7, negative 2. It's always exactly the same process. Right? Take the vector 7, negative 2, write that as a combination of the vectors I and j. So in this case, it's 7 times I plus negative 2 times j. Using the fact that f is a linear function, we can separate over addition. So we have f of 7i plus f of negative 2j. Then again, using the fact that f is linear, it's so useful. We can factor out the 7, we can factor out the negative 2. So we know this is 7 times f of I minus 2 times f of j. And now we know the value of f of I, so we can put 1, 2 down here. We know the value of f of j, so we can put 3, 1 down here. And when we calculate this through, we find that the final value for this problem is the vector 1, 12. Linear functions. Now, in general, you could even derive the formula. You could figure out what the formula is going to be based on this information. Right? So continuing the same example, saying that f is a linear function, right? If we know the value of f of I and f of j, to calculate the general formula, in this case, instead of plugging certain numbers into the function, just plug vector with variables into the function. In this case, the vector xy, we could write that as x times I plus y times j. And again, f is linear, so separate out over addition. And f is linear, so factor out each one of those constants. And we know the value of f of I, so plug that in. We know the value of f of j, so plug that in. And then do your scalar multiplication, vector addition to bring these back together. And there's your formula. And again, just from two pieces of information, you get the formula, and then you can use that on any vector that you want. One of the great things, notice that we have a dot product-like pattern here, something times something plus something times something. It's always a sign there's a matrix vector product lurking in here. You can actually write this function as a matrix vector product. Right? Let that sink in. If f is a linear function, you can write it as a matrix vector product. Right? So to do the most possible general case ever, right? Let's say f is a linear function, and this time, instead of having specific numeric values for f of I and f of j, let's assign variables to these. Right? Let's try to derive something that works in every possible situation. Right, so same process as before. To calculate f of the vector xy, write the vector xy is a combination of vectors I and j. So f of x times I plus y times j. Separate out over addition. Factor out those constants. And then, in this case, f of I we're replacing with a general vector of variables a and c. F of j we're replacing with a general vector of variables bd. And then do your scalar multiplication and your vector addition. You'll wind up with this result, which again you can write using matrix multiplication. Right, so this linear function could be written as the matrix ABCD times the vector xy. So again, I want to emphasize this. I can't emphasize this enough, but I'll try. All linear functions can be written using a matrix. Right? So from two simple properties, which are very reasonable to request, they're very common in mathematics, that once again naturally leads us back to matrix multiplication. And this works both ways, right? If you have a function which is defined as a matrix vector product, that function is a linear function, right? Because any linear function can be written using a matrix. These steps are completely reversible. Matrix multiplication is a linear function. And f of I, right, those values a and c, that turned out to be the first column of our matrix. F of j, those values b and d, turned out to be the second column of a matrix. Right? So if you know that you have a linear function with these two pieces of information, in theory, once you understand this, you can actually just skip right to the end. F of I is the first column of values, f of j is the second column of values. And that's how you can derive the matrix corresponding to a linear function. Now, one of the great things about vectors and matrices, they easily generalize to higher dimensions. So if you have a 3D, a three-dimensional vector, right, in this case, the standard basis vectors are called I, j, and k. There's three of them. They each have three components. And so I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. In this case, once again, if f is a linear function, and if you know the values of f of I, f of j, and f of k, then you're going to be able to write down the formula for f. And it follows exactly the same process as before. There's just a lot more letters here. Right? Any f of x, y, z, to calculate this out, right? X, y, z, that vector as x times I plus y times j plus z times k. Because f is linear, it breaks up over addition, and then you can pull out the scalar multiples, and you'd be left with this expression here, x times f of I plus y times f of j plus z times f of k. Then, since you know the values of the function at the standard basis vectors, you could substitute them in. Then do your scalar multiplications and your vector additions to get this expression. Once again, this looks like dot products, so we could write this as a matrix times a vector. Right? So linear functions, no matter how many dimensions you have, linear functions correspond to matrix multiplication. So as just one more example of the kinds of problems you could do with this knowledge, let's once again say f is linear, and f of I is 7, 5, f of j is negative 4, 6. To find f of 2, 3, right? 2, 3 can be written as 2 times I plus 3 times j. Use your linearity properties to rewrite it like so. Substitute in what you know for f of I and f of j, and then just do the math. In this case, we'll get 14 minus 12, that's 2, and 10 plus 18 on the bottom, that's 28. And so it's pretty quick to calculate a specific value if you know this information. It's also pretty quick to find the matrix equation. Right? F of I is the first column of the matrix, and F of j is the second column. Now, as I like to say, you learn math by doing math, so here's an exercise for you to try out. Assume that f is a linear function. No surprises there, we like linear functions. And assume that f of I is equal to 6, 8, and f of j is equal to 9, 7. Find the value of f of 5, 4, and then write out the matrix equation for f of xy. Kind of like this example right here. All right? And that is linear functions in matrix algebra. Thanks for watching.